sec. Okay, we're live.
Great. Okay, so I'll be chairing the current session. The first talk in this session is going to be given by Philippa Cowderoy on information-aware type systems and telescopic constraint trees. So take it away, Philippa.
Hi everyone. So you've just been told the title already. I better explain what I'm talking about. I got this idea I call information awareness, so I'm going to try and motivate that. Then I'm going to show you some of the tools I use to engage in it. And if I want going to ever give a talk, I'd have to show you something I can actually do. So I'll show you a style of type system, or at least a presentation style that uses them. Then, so the title doesn't make me a liar, I'll also introduce telescopic constraint trees. So, a while back I showed some of my work to my dad, and he couldn't follow the traditional application rule that was simply typed lambda calculus. He was just having trouble putting the two towers that I've got there together and realising, oh, they're the same thing. That's where the answer goes from. I showed him the version on the right, APIC, and he could immediately see how to implement that in Haskell. Now, Dad's not done masses of Haskell, he's done a little, but he can write Fortran in it. And the thing about APIC is that it shows us the information that the inference rule actually infers, that you've got this equality, and we can reason with it, so we can work out that TF must be a function that can take TP as a parameter. More generally, when I see a schematic variable somewhere, I look at it and I don't really know what it says. Is it using known information, or is it a pattern trying to find information out? Is that pattern linear, or is it non-linear? Have I got an implicit equality or something more subtle somewhere? Can I reduce it? Should I reduce it? Am I going to really regret it if I try reducing it? So I want to be more explicit about all of that, and information awareness is what I call the thing we get when we solve some of this problem. And I've got that explicit equality there. It's a constraint. It can help us do better, but using constraints on its own can't stop us from doing worse. Constraint systems in the limited here are incomplete. We can find a whole infinity of ways of confusing ourselves. So, tools for information awareness. The big new one for most people will be information effects, and I'll still be talking more about constraints. So information effects come from a paper called Information Effects by James and Sarbury. They were studying reversible programming. They built a combinator language where instead of functions, the combinators were isomorphisms. So everything was reversible by default. And then they realised they had a new kind of effect that happened if you let yourself break that rule. So you're doing isomorphic programming by default, and information effects are what happen when you stop doing that temporarily. I'm mostly going in one direction only, but that doesn't stop me from using the idea. It turns out to be kind of useful generally. Information effects are breaches of conservation of information in the same sense that we see in physics and quantum mechanics. When information is created, that's an information effect. The same when information is destroyed, and particularly pickily when information is duplicated. So, inference creates new information that's implied by the information we have, and that's the link with type systems. Constraints, I've kind of got this three-pronged view of. There's a syntactic aspect, they have static semantics, they have dynamic semantics. Now the syntax it really is just plain old syntax, it's what we wrote, it's information in the sense of Shannon. But the thing about Shannon is that bits are actually a really bad unit for precise accounting, because, well, you've got that logarithm there, and really you just want the algebra that's before it. The static semantics, what do we know holds if that constraint's satisfied? Possibly what do we know if the constraint can't be satisfied? The satisfaction predicate says whether or not it's satisfied. And also, given the solvers we have available, what shapes of problem can we solve reliably? There's dynamic semantics. A constraint is part of a constraint problem. It's part of the process of solving that problem, which makes it a sub-process that can block on unknown information, or it can provide information. Those unknowns are represented by solver variables or meta-variables. Then the insight for this talk is constraints are kind of a good unit of information. So, on to information-aware type systems. My aims with them, the methods I use to produce them. I'll give you an example for simply typed lambda calculus, and I'll talk kind of a bit about modes. And I might well take a question or two once I've dealt with the modes as well. So, my aims are, I want to be able to see clearly where information is introduced and eliminated. I want to see the data flow. I want to see where I've got a choice about how data flows, whether it's in the design stage, looking at how I put the type system together, or when I'm implementing a type checker. I especially want to know that if I get different results in different directions. I'm going to use linear logic variables for the schema, so there's going to be one positive source and one negative sink occurrence for each variable. I'm going to use constraints because constraint generation is an information effect. They keep the data flow general, and as I've already talked about, they're a really flexible abstraction. And we're going to have explicit duplication because otherwise information effects don't work. You've shoved some of them under the carpet. That'll turn out to be a good thing. So, for the simple typed lambda calculus, I'm going to need a simple type equality constraint. I'm going to need to ask if a given variable is bound to a given type in some context. I need to be able to say some context is what happens when you extend another context with some binding, and I'm going to need to duplicate contexts. Incidentally, I've got some red colouring on here, but so long if you're colourblind, you will be okay. There is no truly critical information contained in the colour. As a convention, I always write left equals right as if I'm assigning to the left-hand side, so patterns go on the left. The context constraints also end up encoding the structural rules. You can change the constraints and end up with a minimal linear system, for example. And then I've got a variable rule which uses the binding in context constraints. I've got a lambda rule where I have to build a context, check it out, and then construct a function type. I've got an application rule which needs to use context duplication, but I'm skipping past those a little bit into modes for the sake of time, and we'll go through those again. So, modes tell us about which way data's flowing. They tell us about when we know enough to solve a constraint, and these things are possibly news to people. The general idea is that data goes positive to negative, and then constraints can fire when all their negative variables are known. There's a bunch of possible modes if you're new to this. We might know everything going in. Our type checker is just asking, does this program make any sense? We might not know the type and we'd be trying to synthesize it. We might not know the context and be trying to figure out the types of free variables. We might even not know the term and be doing proof search, and each of these modes can have its own implementation, what the logic programming crowd call a procedure. The other thing that's worth mentioning at this point is that the function arrow itself is an information effect. It doesn't show up anywhere in the source, and it is in our types. We keep inferring it, so it's information we create to describe our terms. And I give it two different modes based on how I expect the solver to handle equality constraints involving it. so that the left-hand side is still being assigned to. So a positive function arrow is acting as a constructor, and a negative one is acting as pattern matching. As it happens, introduction versus elimination. So, rules again. This time I'm going to make a little bit more effort to explain what's going on. So, we start off with a known context, which is going to flow up to that constraint there. We also know the variable we're starting with. Now that constraint's got all its negative variables filled in, it can fire and finally figure out the type, which it returns down at the bottom again. And all of this is because we're doing this for type synthesis. If we were looking for a free variable types, the data would flow completely differently. The lambda rule is mostly more of the same. Our input term has two identifiable subterms, for example. So x flows up to here. Whereas the initial context goes here, and at this point we now know enough to extend the context into a new one, introducing tau p. We don't know what tau p is going to be yet, but we know we want to use it, so we can talk about it now. Then our extended context flows down here, where we're about to type check the body of the lambda. That fires off and we get back a type. So now we know tau r, we can fill that in. Whoops. We can fill that in here. We've got tau p with whatever we solved about it. From here, that fills in here. That equality constraint can fire, and now we know the type of the function represented by the lambda. Finally, the application rule. The very first thing that has to do, because we're going to check two subterms, is we have to duplicate the context. And one copy goes off to check the function. Ooh, this is going to be messy to highlight. The function. Apologies for this. Over here. And another copy down here. Oh, good, I've got that one. Goes off to type check the parameter. The function goes off to where it's being checked, and the parameter to where it's being checked. And these things have completely separate names. You can see at a glance that they're separate in the same sense as separation logic. These two things can happen completely in parallel. So we figure out the function type, which flows down here, and we're about to pattern match against. We've got the parameter type, which flies in here, and from that, assuming that we got a function at all, we get the type of the result. And that's the application rule done. So this is the point where I said I'd take any questions initially, because I'm about to move on to telescopic constraint trees otherwise. Have we got anything?
Any questions for Philippa? Oops. Seeing if there's any online.
So, I mean, can I just a small clarification then? So it feels like I can essentially read these as an algorithm, right? It's like the program that I would write down. It's much more clear about how to trace things through constraint wise. Is that? That's essentially
Yes.
yeah.
Yes, once we fix the mode, all the data flow becomes fixed, and then it becomes an algorithm. Before we did that, it's still a general type system.
But depending on what we fix the modes for the sort of the conclusion, that will change a lot the rest of the modes for the.
Yeah, the constraint solver may have to do some very different things. If we start out, for example, not knowing the context, and I make you walk the tree bottom up, well, I got thanks from Conor McBride a couple of years back for that one. Anything else, or shall I get on to the really fun party track?
Oh, I thought Tamo was asking a question, but he's on the phone.
Okay.
I think you can carry on.
Yeah, I was about to say, we'll call that his loss, I'm afraid. So, I've done with information-aware type systems, or rather I'm about to use them for something. Now I'm going to talk about telescopic constraint trees, what they are and do, how to build them, and some things to do with them. What is a telescopic constraint tree? Well, it's a tree. It's a refinement of the AST, in fact. It contains constraints, also metavariable binders. It's telescopic in de Brown's sense of telescope, which means it's built out of composable bits of context. And that's composable as in you can write your normal composition dot between bits of it. I'll also sometimes refer to telescopic constraint trees as TCTs for short. Now, what else is it? Well, it's a type checking problem and it's potentially in progress. You can start solving constraints and you don't suddenly invalidate the structure. It's generic. Anything you can sensibly do with the typing rules. If I've built a telescopic constraint tree properly, I can explain in terms of the tree as well. You can derive them directly from an information-aware type system, and they act as a scope-aware constraint store. Now, the simply typed lambda calculus doesn't really care about the scoping. You can just treat all the metavariables as global and run your recurse check and you're okay. You kind of start to care for Hindley-Milner so that you get your generalization in the right order. And when you get as far as dependent types, well, the first time I gave a talk on those, it was to the MSP group at Strathclyde, and I showed the slides to Conor McBride the night before. And I wasn't very clear about whether I was giving him the talk or talking to him about the talk, which led to a cry of, I was doing that 20 years ago. We managed to come to an agreement, which was that he had most certainly been implementing this 20 years ago, but I'd got a logical specification for what he'd been doing for 20 years ago now, and a way of deriving it. So I promise you I'm not just selling you the technology of 20 years ago today. What does it do? Well, it does what an ordinary type checker does, but a telescopic constraint tree does what an ordinary type checker does in time, and it does it in space instead. We do have to alter some of the constraints a bit, because if a constraint refers to the context, it's no good, because we're about to put it in a suspiciously context-like place. So the binding in context and the context extension constraints need reworking. I convert them into one thing which you can think of as a query, or in concurrent constraint programming terms, an ask constraint. What's x bound to here? Or is x bound to tau here? And the other into one which tells the solver they'd better become a binding of x to tau right here. So I call these situated constraints. Their meaning absolutely depends on where they are in the telescope. Incidentally, as a quick cheat, you can solve the tel constraint by just scrubbing out the exclamation mark. Suddenly you have an actual binding for x to tau exactly where it was. I've got the same type equality constraints, but I also need to be able to say, I've got some meta-variable tau I don't know about. And I also need to say, I've got some meta-variable tau, and this is what I know so far. And if I can tell the two apart the way I can with the use of an equality sign or not there, I can ask, is this solved? And I can ask if it's part solved, if the head is solved. Then the really easy piece is that context duplications turn into tree branches. So we build a telescopic constraint tree by traversing the abstract syntax tree. We end up with what I'll call a TCT semantics, which, we've got our brackets around the term, but there's also a type parameter. The idea is to translate the term into a telescopic constraint tree in such a way that tau will become the result type, and to do this retaining all the information that is in the typing rules. And if we can do that, we're golden. So suppose we're doing synthesis again. We're going to need a starting tree just to get us going, which consists of the initial context, a binding for tau saying we don't know what it is yet, but we want to be able to use it in ways that say you know about it. And then we start building the TCT itself using our known term and our known about type meta variable. So tau's acting as a query variable in the sense you might talk about when you're working with databases or again in logic programming. Then with the var rule, we don't know the type yet, so it becomes, we translate the constraint at the top into the one at the bottom. And for subterms, the x we know about here becomes an x we're feeding in here. Then that constraint can fire and we get the tau we know back to return. Building the lambda rule is a bit more involved because there are variables that appear above the line that aren't below the line. So I need an existential binder for both of tau p and tau r. Once I've done that, the equality copies across directly, and then we know we're going to have to check the body. So I insist on the variable binding that corresponds to the top line here, happening down here, before building the tree that corresponds to type checking the body. Then the application rule is more of the same completely, except that we finally have a duplication. So this duplication here splits the contexts. We've got one, which is, this is a pain to highlight. So let's highlight, it'll do the one for the parameter. That becomes the lower of the two branches there, and correspondingly the gamma f branch becomes the higher of the two. Otherwise, the equality constraint is there. We've once again copied out the binders for the variables that we haven't seen. So what can I do with it? Well, I can implement type checkers. I hope I could, or I'd have messed up pretty bad. We can instrument those checkers. Changes in the tree as we start solving constraints show the whole process of solving, including changes in scope, because sometimes we discover a meta variable is more global than we thought. Those changes preserve the AST structure, although we can miss it slightly. We don't have labels around it anymore. So we might want to put those back in as a little bit of an extra information. I think this might make a good UI for type level debugging. We can actually fuse the telescopic constraint tree away a lot of the times. If you suppose we've got a greedy solver for constraints, one that just solves them straight away the moment it sees that, and a tree generator that implements our semantics, we can pick the traversal strategy, and then we can just fuse the tree generator's as a producer to the greedy solver's consumer, and we'll get a traditional checker back. And top down, bottom up, we get our choice. There are times you can't do that. Those exceptions are interesting. Greed doesn't always work. And the reason Conor McBride has been doing this for 20 years is he works with type systems where they don't. We can find and explain some optimizations. One for Hindley Milner, and I think this originally appeared in the Milton compiler. You can have an idea I'll call generalization depth. How many generalization constraints are there from where you are to the root of the tree? You can annotate every meta-variable binder with that depth, and then generalization constraints can generalize variables at the same depth, and generalization is now linear in type size instead of having to crawl back through the context and check for free variables. Anyway, that's pretty much me done. I mean, in summary, information effects unsurprisingly, hopefully, track information well. Constraints are a good unit of information. Information-aware type systems exist, and there's an extended abstract you can read about them in again. Telescopic constraint trees can be derived from them. We can calculate trade-off and optimize from them. But if you remember one thing, telescopic constraint trees do in space what conventional checkers do in time. And that's it. Any more questions?
Thank you very much, Philippa. I guess we can all do a virtual hand clap now. Yep.
Thanks, everyone.
We seem to have a number of questions in Zulip. I'll start with Max. Can you give yours orally, Max?
Sure, yeah. Mine was just the first half of the talk, what you were doing looked a lot like the language in a paper by Uday Reddy, Typed Foundation for Directed Logic Programming. I don't know if you're aware of that paper.
It only rings the loosest of bells, so if you give me...
I linked it in the Zulip, so, but yeah.
Okay, cool. I won't have to Google it
Yep.
then. Thank you very much for the reference.
Okay. I guess let's take a silent question now. Ohad has rather a long one. I'll just read it out for now, and then we can parse it. So, I think we have a notation/description language for the various assumptions/conclusions on inference rules that describe to the constraint solver how to solve the constraints. We know that some collections of, I don't know why we've got collections of again, constraints cannot be effectively solved, perhaps not expressible in your description language. Do you have any proposals or suggestions for a programming language based on your constraint descriptions that gives the programmer tighter control over constraint solving?
I don't quite yet, but I do have an observation, which is that you can tighten modes to the point where they do something a bit like refinement types, so that you can start to have the skeleton of what the parameters are in there, and before you start filling in things as just positive or negative. And I think that's at least a starting point for describing what you can and can't solve, because it gives you a lot more room to say, I can manage that. I don't have anything for combinations of constraints yet. To be honest, I'm still thinking about how I'm going to actually build a general solver for these kinds of constraint problems. It's the kind of thinking where I think I know an answer and I should have coded this up by now, but I'll be coming back to that. I'm hoping I can perhaps get something from the session types community over time.
That sounds interesting. We have another silent question from Chris. I'm wondering if you can compare the approach you're describing here of modeling judgments to that of colored local type inference by Odersky et al. The latter involved coloring type constructors in order to solve subtyping constraints in type argument synthesis.
I don't think I've read that paper in so long that I honestly can't remember enough off the top of my head. What I can say is that you can quite reasonably write rules that are only supposed to be used in specific modes, and that means you can intentionally write a rule, 2 rules, where you're still syntactically directed, but the moment you find out which mode you're solving, you now know which of the 2 you're working with. So, yeah, a little bit like some forms of bidirectional checking. I don't know how closely that ends up involved with the colouring, because it's been that long since I've seen it. So I'm open to an explanation if that's worth bouncing off me, but maybe afterwards.
Yeah, okay, maybe you and Chris can discuss that later. Okay, well, thank you very much.
And thank you too. Just a moment. Done.
So, Chris, can you set yourself up?
Sure thing. Can everyone see that okay?
Yep.
Looks good.
All right.
That's great. Great. So, yeah, our second speaker of this session is Chris Jenkins, and he's going to talk about encodings of Mendler-style co-inductive types in Cedille, and I think has quite a different take to the keynote speaker on what type it look like. So I'm looking forward to this.
All right. Thank you very much. So yes, my name is Chris Jenkins. I'm from the University of Iowa, Department of Computer Science, along with my co-authors, Aaron Stump and Larry Deal. And I'm going to be talking to you about our paper today, Efficient Lambda Encodings for Mendler-style Co-inductive Types in Cedille. So to begin, just a quick review of co-inductive types and their lambda encodings. Co-inductive types or coalgebraic types serve to classify possibly infinite objects, and we understand them as coming with a set of destructors for making observations, a collection of generators, a choice of generators for their production, also known as co-recursion schemes, and we desire productivity of these schemes, meaning that all finite observations we make of them with destructors are well defined. Lambda encodings are an identification of the codata type with a particular co-recursion scheme. So your codata terms are lambda expressions, and your types are defined impredicatively. So you also hear the terminology impredicative encoding. Now, productivity for a given scheme comes for free if the corresponding encoding to that scheme is definable in a total type theory. So why not adopt encodings in settings where this matters, such as in total functional programming or within interactive theorem provers? Well, historically, lambda encodings for inductive types have faced several difficulties, namely those of efficiency and also of logical expressivity. And there's a similar account for the encodings of co-inductive types as well. So considering the case of streams, where we're thinking of efficiency in terms of overhead in the number of observations made, for the church encoding, each use of a constructor incurs an additional linear overhead, and that's because constructors will trigger the regeneration of code data. For the Perigo encoding, there is a flat linear overhead cost because every observation you make involves an additional case distinction. And again, this is just for the case of streams. The overhead can be much worse for other co-inductive types, particular ones where the signature is defined, say, with an inductive type, so certain nested constructions. Now, inefficiency and lack of induction and co-induction in the calculus of constructions, that is the matter of logical expressivity, motivate the development of the calculus of inductive and co-inductive constructions, where primitive data types are added to the theory. But there is a little bit of a trade-off here. Primitive data types with induction swell the trusted computing base. If you have data type declarations within your kernel theory, this means you have to involve positivity checking. If you have fixed point notation for recursive and co-recursive functions, this means they have to do termination and productivity checking. Finally, if you want to support more expressive schemes, this may require further changes to the meta theory. And so an alternative might be to revisit lambda encodings and to try to repair the issues that we just addressed. And this is the project of CDLE, the calculus of dependent lambda eliminations. It's a formally small extension of the Curry-style calculus of constructions that addresses the foregoing issues for lambda encodings, namely that 1, induction is derivable generically for many encodings, and 2, it's possible to define certain very efficient encodings for inductive types. The deal is a higher level language that has special syntax for inductive types that gets elaborated down to the lambda terms and types in the core theory CDLE. So the question, of course, at this point is, well, what's the story about co-inductive types? And that is the subject of this talk. We're presenting a Mendler style of encoding for code data in CDLE that is generic. It works for any positive data type signature. It's efficient. There is no penalty paid for use of constructors, and it's expressive. It supports a combined course of values co-iteration and primitive co-recursion scheme. What is missing in these results are the matter of logical expressivity, namely that these encodings do not support true co-induction in the sense of bisimilarity implying equality. Indeed, we present in the paper a counter result with respect to CDLE's primitive equality type, but of course, index co-recursion for reasoning is supported, and you can see details of this in the paper. What I want to focus on in this talk is just on how we guarantee efficiency for just the primitive co-recursion scheme. In particular, what the Mendler style of coding co-recursion is and how it helps, and the two techniques we use to ensure efficiency. One, fairly standard monotone fixed point types a la Matisse, and the other is a CDLE specific technique, proof irrelevant type inclusions. Okay, so let's take a look at this formulation of co-recursion schemes that the encoding is based on, the Mendler style. For every classic or conventional co-recursion scheme, there is an equivalent Mendler style scheme. Now, the advantages of the Mendler style have been well studied in the past couple of decades, but just as a short summary, it's more idiomatic for functional programmers because you are making your co-recursive calls explicitly in the same style as you would with general co-recursion. And in particular, the Mendler style formulation avoids the buildup of intermediate structures that occur in more complex schemes expressed in the conventional style. And indeed, the fact that they were avoiding this building up of these intermediate structures just to tear them down during observations is what helps us, what assists us in the efficiency gain. Taking a look at just the simple co-iteration scheme for the generation of streams, in the classic formulation, this is done by taking some type S, which we're going to think of as a state space, and along with this type, we provide two operations. One, H, which is a function that says, given the current state of the stream, tell me what the head element is. And the other, T, which we can think of as a state transition. Given the current state of the stream, give me the state associated to the tail of the stream. Indeed, looking at the operational semantics, which are here described as saying what are the observations defined for the stream generated by co-iteration. If we take the tail of the stream generated by classic co-iteration, we find that it's what we get when we take the initial state, the given state S, take one step with a transition function T, and then generate the stream out of that. The conceptual leap that occurs in the Mendler style formulation is how we think of T. Instead of having it be a state transition, we can think of T rather as a stream generator transformer, and one that has this parametric property. So T is now a higher order polymorphic function quantifying over a type argument R. Taking functions of type S to R, where we're thinking of this function as a way of generating streams from R. So R is sort of a stand-in for recursive occurrences of stream A itself. I'm taking such stream generator functions and transforming them to another. Looking at the operational semantics, we see that indeed the tail of the stream so generated is given by taking T, instantiating the type argument R to stream A. We must now provide a function of type S to stream A, but this is of course exactly what the Mendler style combinator for co-iteration gives us. And finally, the given state S. To look at how the Mendler style formulation helps to avoid the buildup of intermediate structures, let's take a look at the slightly more complex scheme, the primitive co-recursion scheme. The idea behind the scheme is that you want to short-circuit the generation of code data by returning some pre-made values. So in the case of streams, we might be generating, say, the first 100 elements of the stream, and then decide that the rest of the stream can be given by a stream that was already created. The way that this is done in the conventional formulation is to have T return a coproduct, where on the right-hand side, you're still considering the values of type S as the state of the tail. But on the left-hand side, if it's a left injection, then this is our early exit conviction. In the operational semantics, this is done by doing a case distinction on the value returned by T of S. And indeed, if it's a first injection, we just return the given stream. Otherwise, we continue generating. In the Mendler style formulation, instead of introducing a coproduct, we provide the generator transformer another argument, another way of creating values of type R. So now, instead of creating these values from just S, we allow the user to provide, to take given some pre-existing stream A and inject this into the type R. So before I said R is standing in for the type stream A, now we can refine this intuition a little bit and kind of think of R as being a certain super type of stream A. In the operational semantics, again, instantiating the type argument R to stream A, we see that now this additional argument obligates us to provide a function of type stream A to stream A. And of course, this is easily given by the identity function. Noting here, in the case of the Mendler style formulation, you see that there is still this additional beta redex. But in the next section, I'm going to show that even this, a little bit of overhead can be completely removed in CDLE. All right, so now let's take a look at how this is achieved using monotone recursive types and proof-irrelevant type inclusions. If we were to try to read an imperative encoding off of the rules governing the Mendler style primitive co-recursor combinator, we would find that we seem to need recursive types, and indeed there's no other known way to achieve this. This is because we want to take the types of the terms occurring in the premises of this rule and use it as a definition of stream A, and wouldn't you know it, stream A would occur recursively in the definition. As a refresher for a type scheme F, a recursive type μF is one such that there exist these two operations, roll and unroll. Roll we think of as taking an F collection of μF predecessors and constructing a successor value. Unroll undoes this, taking some value and unraveling it into its F collection of predecessors. And indeed, by undoes this specifically, we must have the following computation rule, that unroll of roll of T should reduce to T. This is also called the beta law for recursive types. Of course, unrestricted recursive types lead to non-termination in your theory, and the culprits are these type schemes F that have negative occurrences in their type argument. So of course, we can use a syntactic notion of positivity to recover termination, or what we will be using here is a notion of monotonicity and monotone fixed point types. Of course, the notion of F being monotone in a pre-order is that for any two elements in the pre-order, X being less than Y implies that F of X is less than F of Y. If we want to generalize monotonicity to type theory, we need some way to interpret this less than or this ordering operation and implication. And of course, you can interpret monotonicity in system F already by interpreting both of these as a function space. But for recursive types, this would lead us back to Church encodings. And of course, the problem there is that the beta law for recursive, the beta law for these types would not be satisfied. That is indeed a more general statement of the problem of the inefficient predecessor for Church numerals. So the CDLE twist is going to be to choose a different interpretation. For the ordering operation, we are going to use a notion of type inclusion, here written cast ST, which we interpret as saying that every term of type S also has type T. For the notion of monotonicity, we are going to have a listing of type inclusions over the type scheme F, but in a way that's done it's going to be done in a proof-irrelevant fashion. So let's talk about this notion of erasure and proof-irrelevance. So again, CDLE is Curry style. Type annotations are external to the real term language, which in our, philosophically, which we view as the untyped lambda calculus. And so all of these are erased. Indeed, definitional equality is defined up to erasure. So this polymorphic identity function over on the left-hand side and this identity function on T on the right-hand side, both erase away, to the untyped lambda calculus term lambda XX. One of the ways in which CDLE extends the calculus of constructions is that not only type arguments, but term arguments to functions can be irrelevant also. This is written here as t. Little t has type t prime open arrow t to mean that t is a function taking some t prime argument, but the t that it returns doesn't depend at all upon the choice of the given argument. Syntactically, for applications, we write that we write application of a function to its erased argument with a hyphen, and the erasure of this expression is just erases away to the function itself. So the argument that occurs in this application disappears. Type inclusions, cast st, are a derived notion in CDLE, but for brevity, I'm presenting them here axiomatically. You can see full definitions in the appendix. For the purposes of the talk, I just want to focus on these two properties: the derived elimination form and its erasure. So if I have a witnessed that there is an inclusion of the type s into the type t, then I can convert this into a function from s to t, of course. But what's important about this rule is that the use of the function does not depend upon at all on the particular choice of the witness. Indeed, the elimination form here erases to lambda xx. And of course, the idea behind this is that if every term of type s has type t, if I want to write a function that converts between the two of them, I take some given term of type s, and then I just return it because it already has type t. So the takeaway here is that type inclusions are computationally irrelevant. Then we can define monotonicity, again, as a lifting of type inclusions over type schemes and get this derived elimination form and its erasure. Elim mono gives us a function of type f of s to f of t if we know that f is monotone and we have a witness of the inclusion of s into t. And again, this monotonicity witness is also erased, and the erasure of the elimination form elim mono is just lambda xx. So the takeaway here is that monotonicity witnesses are also computationally irrelevant. Finally, using standard techniques, we can define the recursive type form or rec with a constructor and destructor. What we see here is that both roll and unroll do require proofs that f is monotone. However, their definitions do not depend upon the particular choice of proof. And indeed, that's because roll and unroll witness a two-way type inclusion between the types f of recf and recf. They both erase away to the identity function, and as a consequence, the beta law is trivially satisfied because then the statement is a composition of identity functions, operates extensionally like the identity functions. All right, so now I want to take a look at the generic encoding, not getting too much into the details, but just really pinpointing where the technique is guaranteeing us efficiency. So by generic, I mean parametric. We're working with a type scheme f and a witness that f is monotone. For simplicity, the type definitions I'm showing you here for the encoding have had the support for course of values co-iteration stripped out, but you can again see the paper for the full definition. The first type definition is coalgebra. Of course, it's the generalization of the shape of the scheme for co-recursion. S is still our type parameter representing the state space, the given state space. But C is now the parameter which we're taking our fixed point. This is still a polymorphic function quantifying over type arguments R, types R. Before we had highlighted before a function of type stream A to R when we were looking at streams. Now we're talking about an inclusion of the codata type into R that is given as an erased argument. So again, proof irrelevant. Then we can define our codata type new using recursive types and this existential encoding. If you have not seen this before, this is a standard way of defining greatest fixed points in type theory impredicatively. And noticing here that this type scheme is positive in the type argument C, we can see that we can define roll and unroll. We can use roll and unroll to define the generator and destructor, unfold M and out M, satisfying the following typing and computation rules. In particular, in the computation rule, I have that if I make an observation without on the stream generated by unfold M with C and S, I take my coalgebra C, instantiate the type argument R to new. My obligation is now that I must provide a proof that new is included into itself, And of course, this is easy because every type has by an easy lemma, every type is included into itself, followed by the handle for making co-recursive calls and the given state. But notice that here below, what we had before was an additional application to lambda XX, and now is an argument to, this is a application to an erased argument. So there's indeed no overhead for primitive co-recursion here. But that's not the only thing we wanted to guarantee, right? We also wanted to make sure that the use of a constructor did not introduce any overhead either. So we can we take a look now at the definition of NM. It has a type f of new to new. In order to define it, we do use the generator unfold m, choosing as a state space the type f of new, introducing our assumptions of type argument r and inclusion and g. G has type f of new to r, and this again is our handle for making co-recursive calls. If we were to use G in order to construct a value of type f of r, then we would have failed in our goal, because this would mean that we were co-recursively regenerating data at every observation. So instead, we take a different approach. Our obligation, again, is a function of type f of new to f of r. We have a proof, a witness that there's an inclusion of new into R, and a witness that the type scheme f is monotone. So that means that we have an inclusion of f of new into f of r using the derived elimination form of lim mono. This gives a function of the appropriate type that erases away to lambda xx. As a consequence, the following operational rule, or 1/2 of lambda x lemma, if you're familiar with the statement, out m of nm of t reduces to t for all terms t. There is no regeneration of codata, which is what you would see in the church encoding, or if we were to use g here in this expression. And indeed, there's no traversal over the type scheme f with fmap, which is what you would see in most encodings and pretty much any other type theory that does not have equivalent notions. And again, I mentioned at the outset that if your signature for your codata type was a list, then fmap would be a list traversal, and then every observation would, could be quite expensive potentially. But here, none of that happens. It's just an identity function, a type coercion function. So there is no penalty for the use of constructors at all. So in conclusion, we presented a generic derivation of codata in CDLE, supporting an expressive co-recursion scheme efficiently. In order to do so, this required a different approach than what we have used previously for efficient inductive types, namely leaning on monotone recursive types a la Matis. The termination guarantee, so there is a proviso here. The termination guarantee in CDLE is somewhat subtle. It holds for closed terms, which can be assigned a function type. And if you're hearing that and thinking, well, wait a minute, well, then it can't be a true type theory. Well, yes, this is a bit of a caveat, but the condition does hold for all closed terms of data and codata, all closed terms which we would consider as data and codata, but computing with open terms is in general unsafe. Indeed, the feature that we use to guarantee efficiency, one of the axioms in CDLE, contributes to this proviso. Now, for future work, we are actively working on an encoding that supports co-induction up to an equivalence relation that's derived from binary parametricity, rather than trying to do this up to CDLE's primitive equality type, which is what we use in the counterexample. That's more of the semantic side. On the syntactic side, we're looking at designing a nice surface language for codata that involves co-pattern matching and using coercive subtyping to infer the insertions of these type inclusions. But the Mendler-style formulation does help to bridge the gap between syntax and semantics because productivity checking is reduced to type checking while maintaining a familiar style of making explicit co-recursive calls. All right, and that's my talk. Thanks.
Thanks, Chris. Okay, I'm just going to see, are there any questions in Zulip? Yes, there is. Okay, there's one silent question from Pierre-Marie. He says, can you give an intuition for the example that bisimilarity is distinct from equality? Is it due to the use of continuation parsing style in a nonlinear way? i.e. availability of control operators in Mendler style?
Yeah, so I don't think that it has much to do with that. It has more to do with the fact that CDLE's primitive equality type is anti-extensional. So if you're, the ideal notion of equality for co-inductive types is equivalent behavior. But of course, you can have two state machines, say, that have different internal configurations that generate the same behavior. But if you state that two terms are equal up to CDLE's equality type, this is literally intentionally equal. So this is how it arises the counter example.
Okay. Any more questions? Tarmo has a silent question. He says, "Thank you for the very clear talk.
Thank you.
Can you comment on what is the status of CDLE's very powerful meta theory today? What has been proved about it, and what has been proved with pencil and paper, and what has been proved formally?" I think he means mechanized.
Right. So we are currently working on we have a project involved of formalizing CDLE in Coq, as well as a translation of a subset of Coq into to CDLE. But there are no results results currently to present as far as mechanization. Concerning the meta theory of CDLE, of course, it is consistent as interpreted as a logic, and we have the termination guarantee as well. That is not, of course, it's not complete for it does not hold for all open terms, but it does hold for closed terms. So these are the essential to meta theoretic properties.
Okay. I guess following up on that, I have a maybe slightly higher level question, which is you get this nice performance improvement with these encodings, no overhead at all. That's great. But what, if anything, would you say you're paying for in terms of your ability to reason about programs?
So I suppose, yeah. I'd say, are you asking more? So you're asking more like, what do you pay for having to do this within the setting of CDLE itself, or anything particular about the encoding?
Well, say if you want to prove some property about a CDLE program, is it made any more difficult by the particular kind of encoding you're using, or is that are you sweeping some details under the hood by using these fancy encodings, or does it just work out just as well as it would if you were trying to formalize the same thing in Coq or something?
So I would say that for the choice of the particular encoding, it works out. It works out quite well. The more, and this is because the more you rely on erasure, the more essentially, when you're proving something about about a program in CDLE, you're really talking about the underlying untyped lambda calculus term, and the more you lean upon erasure for your operations, the simpler the underlying encoding is. So there are, of course, CDLE, the meta theory lacks large eliminations. So there are limitations to working within the theory itself. But as far as the encoding is concerned, I can't say that I've encountered any real technical difficulties with this. It's actually quite simple.
Okay, thank you. Any more questions, either on Zulip or live in Google Meet? Okay, in that case, let's thank Chris